Hello, and thanks for using TickBoom. In this question, I'm focusing on part 2 of this 5-part question, and this video follows on directly from a prior video where I'd already worked through part 1 and given a bit of background to this question. So if you haven't already looked at that video that goes through part 1, I recommend you take a look at that first before working through this video. Now in terms of background to this question, I did mention in the first video this question was sent through to me from a student who encountered this on a test they did at Baulkham Hills High. Since recording that video, I've also learned that this question originally came from a trial paper that was prepared in 2019 by a few mathematics Olympiad medalists. So I think that kind of helps explain why this question is so difficult. Gives a bit more context around that. This question was actually part of what was question 16 in that exam, and question 16 is always typically the hardest question on the 4-unit paper. So it's no surprise that this question is so challenging, particularly part 5, which still, at the time of recording this video, I still haven't cracked. But what I'll do now is I'll focus on part 2. Part 2 is asking us to prove that every integer for n greater than or equal to 2 satisfies the relationship 1 on 2 to the 2/3 plus 1 on 3 to the 2/3 plus all the way up to 1 on n to the 2/3. That sum we want to show is less than or equal to the integral from 1 to n of x to the negative 2/3 dx. So we want to show that as part 1 of this. And from there, show that x n plus 1 is greater than 1 on 3 times the cube root of n minus 1 for each integer n greater than or equal to 2. Now, the challenge with this question, particularly from parts 2 onwards, is that it's really hard to know where to start and what techniques you should try and apply to do this proof. It might be tempting to think we could try induction again, but whilst that helped for part 1, it's not going to help here. And after racking my brain for a while, eventually I got to a place where I thought, well, that integral there gives a little hint as to how you can think about this question. We've got an inequality. On one side, the right-hand side is an integral, and on the other side is the sum of a whole bunch of numbers. Now, I eventually started to think, well, when I first learned about integration, I learned that the integral is the area beneath the curve. And in having that introduced to me, we looked at a curve, whatever that curve was, and we started drawing rectangles underneath that curve. And those rectangles would approximate the area under the curve. And as those rectangles got thinner and thinner, they get closer and closer to approximating the curve, but in general would always be less than or equal to the curve. So that got me thinking perhaps a diagram could help as a starting point for this question. So that's what we'll do. I'll just write out what we're trying to show. So for this part 2, we want to prove that 1 on 2 to the 2/3 plus 1 on 3 to the 2/3 all the way up to 1 on n to the 2/3, that's less than or equal to the integral from 1 to n of x to the negative 2 on 3 dx. That's what we're trying to show. And what I'll do is I'll just draw up a chart that will help us think about this. So we'll go 1, 2, 3, 4, go n minus 1, n, go 0.2, 0.4, 0.6, 0.8, 1. And what I'll do to start is I'll just start plotting the various values. We're concerned with between 1 and n, so between 1 and n. So 1 to the power of negative 2/3 is just 1. 1 to the power of anything is 1. But what I'll do now is I'll just key in some of these values to see what we get and see what curve plots. So I'll just go 2 divided by 3 and I'll store that. And we'll start with 2 to the power of negative 2 on 3 is 0.62. And 3 to the power of negative 2 on 3 is just under 0.5. 4 to the power of negative 2 on 3 is just under 0.4. And you kind of, it's probably enough to see the pattern. We kind of have a curve that looks broadly like this. And we know that the integral between 1 and n represents, well, this shaded area under the curve represents that integral. Now, as I mentioned, when you first learn about integration, you kind of do this exercise where you draw rectangles under the curve. And in theory, those rectangles, if they get thinner and thinner, they get closer and closer to approximating the area under the curve. So what I'll do is I'll just draw some of these rectangles. Because by visual inspection, we can see that the area of these rectangles will always be less than the area under the curve, or if we could get them thin enough until they're infinitely small, they'll be equal to the curve. So I'll just write that. I'll say the area under the rectangles is less than or equal to the area under the curve. Now the area under the curve we know is the integral, so that's easy enough and we can leave it in that format. But the area under the rectangles, we can make use of the rule for area of rectangles, which is just the height times the width. In our case, the width is always 1. So the area under the rectangles is, this is 2 to the power of negative 2 on 3. So that's 1 on 2 to the 2/3 times 1, plus 1 on 3 to the 2/3 times 1, plus all the way up to, that's a height n, so 1 on n to the 2/3 times 1. That area is less than or equal to the integral from 1 to n of x to the negative 2 on 3 dx. So this simplifies very easy, it's all times 1, so we get 1 on 2 to the 2/3 plus 1 on 3 to the 2/3 plus 1 on n to the 2/3 less than or equal to the integral from 1 to n of x to the negative 2 on 3 dx. And that is what we were asked to prove. So actually, after kind of getting to the point where you can think to draw the diagram and visually inspect, the proof actually becomes very simple, at least of this first part. Really not a lot to it. So the real challenge in that question is thinking to do this in the first place, and that's what can take the time. If it springs to your head right away, you know, you'll do well. But if you spend a lot of your time in the context of an exam kind of hitting a brick wall and not knowing where to start, that's where you could perhaps miss out on these marks, because whilst in the end the proof is very straightforward, it just might not come to you. For me, the light bulb moment came when I saw the integral in the inequality. That made me think, well, what is an integral? What's the definition? Area under the curve. That's going to help me. Now that's only the first part of this question. The second part was to show, we wanted to show that xn is, xn plus 1 is greater than 1 on 3 times the cubed root of n minus 1 for n greater than or equal to 2. And the question says, hence show that. So it's kind of alluding to the fact that what we've just proven, we should make use of that to then prove this next step. Now, what I think can be helpful here is if we take a look at what we demonstrated in part 1 using induction, that result, we know if x to the n is less than or equal to 1 on the cubed root of n minus 1. That's what we've proven in part 1 for n greater than or equal to 2. If that's true, then we can know that x to the n squared will be less than or equal to 1 on n minus 1 to the 2 on 3. So, and that's also for n greater than or equal to 2. The cubed root of n minus 1 is n minus 1 on a third. When I square it, I get 2/3. Very similar to what we've seen earlier. So now if I just think about writing this out for each of our results, we'll start with x2. x2 squared would be less than or equal to 1 on 2 minus 1, 1 on 1. x3 squared would be less than or equal to 1 on 3 minus 1 is 2, 2 to the 2 on 3. x4 squared would be less than or equal to 1, 3 to 2 on 3, and so on, all the way up to xn squared would be less than or equal to 1 on n minus 1 to the 2 on 3. So that's all things we know from what we proved in part 1 of this question in the prior video. If that's the case, we can say therefore x1 squared plus x2 squared plus x3 squared all the way up to xn squared, that must be less than or equal to x1 we know is 1, so 1 squared is 1, plus x2 squared we've also seen is 1, plus 1 on 2 to the 2/3 plus 1 on 3 to the 2/3 plus all the way up to 1 on n minus 1 to the 2/3. And that hopefully looks familiar. This part here is very similar to what we've seen here. All it is instead of going up to n, we're just going up to n minus 1. So if just over to the side, I say this is less than or equal to the integral from 1 to n minus 1 of x to the negative 2/3 dx, which is equal to, so we'll get x to the third on a third from 1 to n minus 1, which will give us 3 times n minus 1 to the third minus 1, and I'll just write that as 3 n minus 1 to the third minus 3. So that we know if x1 squared plus x2 squared and so on is less than or equal to 1 plus 1 plus this, and if this is less than or equal to the integral, then we know that if we insert the result of this integral in, the inequality will still stand. So therefore we can say it's less than or equal to 1 plus 1 plus 3 n minus 1 to the third minus 3, which is just this, inserting that, which is less than or equal to 3 n minus 1 to the third. 1 plus 1 minus 3 is minus 1. Now if this series is less than or equal to that minus 1, if I don't subtract the 1, it must definitely be less than 3 n minus 1 to the third. That inequality will hold true. If I don't subtract the 1, what I've got will definitely be less than this. So now what I can say is I can kind of take the reciprocal of each side, and what I'll get is 1 on 3 to the n minus 1 to the third would be less than 1 on x1 squared plus x2 squared plus all the way up to xn squared. Now if you think about the definition of our recursive relationship, that is the definition of x n plus 1. So now just kind of rearranging this, we get x n plus 1 is greater than 1 on 3, and I'll just write it in the format. They've got the cubed root of n minus 1. Cubed root is the same as to the power of a third. So there we've shown what we were being asked to show for n greater than or equal to 2. And I've demonstrated that by starting with the result that we proved in part 1 of the question in the prior video, and then getting something that had a format that allowed us to make use of what we'd just shown in the first part of this part 2. So you can see how this is quite a well-written question, because each part that we prove allows us to tackle the next part of the question, and we'll see that pattern as we go through the rest of the parts of this 5-part question. But that's all I've got to say for this part 2. Hopefully you were able to follow along with that. The real challenge, I think, of this question is thinking, or being able to think, have that light bulb moment that this integral is the area under the curve. From there, it really is just straightforward algebra from there. There's room to make a few mistakes, but as long as you're careful and cautious, don't make mistakes with your algebra, think about your inequalities, you can get there. So I think this is kind of helping to show this is a very elegant, well-written question, which kind of is no surprise given it's Mathematics Olympiads medalists who wrote it. But yeah, it's a very interesting question to work through. So hopefully you have been able to follow along with that. I'll move on to part 3 in the next video, so stay tuned for that. And tick boom.